Good morning. Here's your daily tech briefing for 2026-08-23. Today we're covering Java, Hibernate, Redis, Docker, Kubernetes, and Cloud, AWS/Azure/GCP, plus the Architect's Corner. Let's get into it. Let's dig into a couple of Java-focused items that have been bubbling up on the dev community boards. First up is a nuanced discussion that's been sparking on Stack Overflow about the difference between static final fields and the JVM flag called TrustFinalNonStaticFields. At a glance, both of these concepts touch on how the Java virtual machine treats fields that are declared as final, but they do so in quite different ways. A static final field is the classic constant you've probably used 100 times. When you write something like static final int max retries equals 5, the compiler knows that the value will never change after the class is loaded. Because of that, the value can be inlined directly into the bytecode wherever it's referenced, which eliminates the need for a field lookup at runtime. That inlining can give you a tiny performance boost and also guarantees thread safety without any extra synchronization, because the value is immutable by definition. Now, the TrustFinalNonStaticFields flag is a bit more esoteric. It's a JVM option you can enable at startup, and what it does is tell the just-in-time JIT compiler that it can treat non-static final fields as if they were immutable after the constructor finishes. In plain English, the JIT will assume that once an object is fully constructed, any final fields on that object won't be changed, even though the Java language spec only guarantees immutability for static final fields. The benefit is similar to static finals. The JIT can cache the value or fold it into optimized code paths, which can shave off a few nanoseconds in hot loops. The Stack Overflow thread points out the trade-offs. Enabling TrustFinalNonStaticFields can improve performance for code that heavily reads final instance fields, but it also opens a subtle risk. If you use reflection, unsafe tricks, or bytecode manipulation to modify a final field after construction, something that's technically possible but discouraged, the JIT may have already baked the old value into optimized code, leading to inconsistent behavior. In practice, most well-behaved applications never mutate final fields, so the flag is safe. But the discussion warns you to be aware of any libraries that might be doing low-level field hacks. The consensus is to enable the flag only when you have measured a real bottleneck that stems from final field reads, and when you're confident that no part of your stack is tampering with those fields. Switching gears, the second item is a project called Chainwarden, which landed a fresh release aimed at Java developers who need to validate cryptocurrency addresses offline. The core problem Chainwarden tackles is that many blockchain wallets use checksums or base 58 encodings that are easy to get wrong. Traditionally, services would call out to an external API to verify that an address looks legitimate, but that adds latency, introduces a network dependency, and can expose user data to third-party services. Chainwarden bundles a set of pure Java validators for a wide range of coins. Think Bitcoin, Ethereum, Litecoin, and dozens of ERC20 tokens. Because the library runs entirely locally, you can validate an address in a single method call without leaving your server. That's a big win for payment gateways, exchange backends, or any microservice that ingests user-provided crypto addresses. It reduces response times, keeps your architecture simpler, and eliminates a class of failure where an external validator goes down or throttles your traffic. The library also handles edge cases like mixed-case checksums for Bitcoin Cash or the newer Betch32 format for SegWit addresses. By catching malformed addresses early, you avoid costly downstream errors, such as sending funds to an. Hibernate just rolled out 2 new point releases, one for the 7.4 line and another for the 6.6 line, and they're worth a quick look if you're keeping your JPA stack up to date. First up is Hibernate ORM 7.4.6 Final. This is the latest patch on the 7.4 series, which is the current long-term support branch for most new projects. The release notes point you to the full change list on the Hibernate JIRA. But even without digging into every ticket, you can expect the usual mix of bug fixes, performance tweaks, and small feature refinements that keep the ORM stable under heavy load. What's practical for a backend engineer is that 746 continues to support Java 17 and newer, and it maintains compatibility with the latest versions of the major databases: PostgreSQL, MySQL, Oracle, you name it. If you've already upgraded to 745, the migration guide linked in the announcement tells you there are no breaking schema changes, just a handful of deprecations that you might want to clean up before the next major version. In day-to-day work, that means you can drop the new jar into your Maven or Gradle build, run your integration tests, and you should see the same behavior, but with a few hidden bugs squashed. Things like occasional session leak warnings and edge case lazy loading failures that have been reported in production environments. The second release is Hibernate ORM 6.6.56, final, the latest patch for the 6.6 branch. That line is still widely used in legacy applications that haven't moved to the newer 7x series, often because they're tied to older Java versions or specific vendor extensions. Like the 7.4 release, the 6.6.56 notes direct you to a JIRA filter showing every issue that was resolved. The key takeaway is that this patch is primarily a maintenance release. It addresses stability problems that have surfaced in long-running services, especially around connection pooling and the second-level cache. If you're running a Spring Boot application that still pulls in Hibernate 6.6, updating to 6.6.56 is a low-risk way to tighten up those corner cases without having to re-architect your data layer. Both releases also link to a What's New page on the Hibernate website. Those pages usually highlight any new annotations, query language enhancements, or support for newer JDBC drivers. Even if you're not planning a full upgrade, it's worth scanning those sections to see if any of the newly supported database features could simplify your code. For example, native JSON column handling that some drivers have just added. Finally, the migration guides for each line give you a checklist of things to verify after the upgrade. Confirm your dialect settings, rerun schema validation, and watch the logs for any deprecation warnings. In practice, most teams can roll these patches out in a rolling deployment, run their smoke tests, and be confident that the ORM layer is now a little more robust. So, if your POM XML still pins Hibernate at 7.4.5 final or 6.6.55 final, consider bumping it to the newly published 7.4.6 final or 6.6.56 final and let the bug fixes do their work. If you've been juggling a mix of databases for local testing, you might have seen a new project pop up on Hacker News called Wharf. It's an open-source toolbox that lets you spin up PostgreSQL, MySQL, MongoDB, ClickHouse, and importantly for us, Redis, all inside Docker containers with a single command. The idea is to give developers and DevOps engineers a quick, reproducible way to stand up the exact data, services they need, without manually pulling and configuring each one. What makes Wharf interesting for Redis users is the way it abstracts the usual Docker boilerplate. Normally, you'd write a Docker compose file, map ports, set up volumes for persistence, and maybe tweak a few environment variables. Wharf bundles all that into a tiny configuration file and a helper script. You can start a Redis instance with the default settings in a matter of seconds, which is perfect for unit tests, integration suites, or a sandbox environment where you need a clean slate each run. From a practical standpoint, this helps keep your CI pipelines lean. Instead of maintaining separate Redis containers for each project, you can point your test suite at the Wharf managed Redis, reset the data between runs, and be confident the environment matches what you'd get locally. Because it's Docker-based, you still have full control. You can mount a volume if you need persistence for a longer-running dev environment, or you can pass custom Redis configuration flags through the Wharf CLI. That said, Wharf isn't meant to replace a production-grade Redis deployment. The default setup runs with no password and minimal persistence, which is fine for development, but would be a security risk in production. For production workloads, you'll still want a managed offering like AWS Elasticache, Azure Cache for Redis, or a self-hosted cluster with proper replication, backup, and monitoring. In short, if you're looking to streamline the way you spin up a Redis instance for testing or local development, give Wharf a try. It reduces the friction of Docker orchestration, keeps your environment consistent across machines, and lets you focus on writing code rather than fiddling with container configs. Just remember to switch to a hardened, production-ready Redis setup when you move beyond the dev sandbox. Imagine you've got a fresh Docker host sitting on a spare VM, and you want to turn it into a versatile playground for a few niche but surprisingly useful tools. The first one that's been bubbling up on Hacker News is called Neko. At its core, Neko is a self-hosted virtual browser that lives inside a Docker container and streams its display over WebRTC. A virtual browser is just a headless instance of Chrome or Chromium that you can interact with remotely, kind of like a remote desktop for a web page. The magic here is WebRTC, which stands for Web Real-Time Communication, a set of browser APIs that let you send video, audio, and data directly between peers without a middle server. By packaging the browser together with a lightweight signaling server into a Docker image, Neko lets you spin up an isolated browsing environment in seconds, then connect to it from any modern browser on any device. That's handy for a few real-world scenarios. You can run a browser sandbox for testing sites that might be risky. You can let a client view a demo without giving them direct access to your internal network, or you can set up a shared screen for collaborative debugging. Because it's containerized, you get the usual Docker benefits: quick start-stop cycles, reproducible environments, and the ability to enforce resource limits so the browser never hogs the whole host. The project is open source on GitHub, so you can inspect the code, tweak the Docker file, or even add your own authentication layer if you need tighter security. The second project making the rounds is Wharf, another show HN entry that bundles a collection of popular databases: PostgreSQL, MySQL, MongoDB, Redis, and ClickHouse, into a single Docker-based deployment. Think of it as a one-stop shop for self-hosting the data stores you'd normally spin up individually. Each of those databases serves a different purpose. PostgreSQL and MySQL are relational databases, great for structured data and complex queries. MongoDB is a document-oriented NoSQL store, useful when you need flexible schemas. Redis is an in-memory key value store, perfect for caching and fast pub/sub. ClickHouse is a column-oriented analytics engine designed for high-speed OLAP queries. By wrapping them all in Docker, Wharf gives you a consistent way to bring up a full-stack data environment with a single command. For a backend engineer, that means you can spin up a realistic test environment on a laptop or a CI runner without juggling separate installers or cloud credentials. It also helps teams that prefer to keep data in-house for compliance reasons. Rather than reaching for a managed cloud service, you can run the same stack behind your firewall, with the same version pinning you use in production. Because it's just Docker, you can leverage Docker Compose or Kubernetes to orchestrate the containers, apply health checks, and define resource quotas. The project's GitHub repo includes example configurations, so you can see how each service is wired together, and you can replace any component with a custom image if you have specific extensions or plugins you need. Rounding out the trio is ServerKit, a self-hosted control panel that aims to bring a bit of the one-click app experience you get from cloud platforms into your own infrastructure. The idea is simple. You run ServerKit in a Docker container, and it gives you a web UI where you can manage applications, Docker containers, and databases without typing a lot of CLI commands. For a DevOps engineer who's comfortable with the terminal but still wants a quick visual overview of what's running, this can be a real-time saver. The panel lets you spin up new containers from templates, attach volumes, set environment variables, and even provision a database instance from the same list that Wharf offers. It also provides basic monitoring, CPU, memory, and network usage, so you can spot a runaway container before it eats up your host's resources. Because everything runs inside Docker, you can sandbox the control panel itself, upgrade it by pulling a newer image, and roll back if something goes sideways. The project is also open source, which means you can audit the code, add your own authentication backends, or integrate it with existing CI pipelines. In practice, teams have used similar panels to give developers a safe way to experiment with new services without needing admin rights on the host, while still keeping the underlying infrastructure under the ops team's control. All three tools share a common thread: They take the flexibility of Docker and layer on a user-friendly experience that reduces friction for everyday engineering tasks. Neko turns a headless browser into a shareable sandbox session, which can be a boon for security testing or remote collaboration. Wharf consolidates the most common data stores into a single, reproducible stack, cutting down the setup time for local development and CI environments. ServerKit adds a lightweight control surface, so you can spin up, monitor, and manage those containers without dropping to the command line for every little change. For a backend or DevOps professional, the practical takeaway is that you don't have to choose between raw Docker power and ease of use. You can adopt these community-driven projects to get the best of both worlds. And because they're all open source, you can tailor them to fit the exact policies and workflows your organization follows. If you've been wrestling with Kubernetes security for any length of time, you know the audit process can feel like a scavenger hunt through a maze of manifests, role bindings, and network policies. A new open-source project called K8's Audit is trying to shrink that hunt down to a 30-second check, and it does so using only two tools you probably already have on your workstation: Kubectl, the command line client for talking to a cluster, and JQ, a lightweight JSON processor. The idea behind K8's Audit is simple. It pulls the current state of your cluster with a single Kubectl get command, pipes the raw JSON output straight into JQ, and then runs a series of predefined filters that look for common misconfigurations. For example, it will flag any service account that has the cluster admin role attached, highlight pods that are running as the root user, and point out network policies that are missing entirely in namespaces that should be isolated. Because it's just a shell script, you can drop it into a CI pipeline or run it locally before a production rollout, and you'll get a concise report in under half a minute. Why does that matter? In many organizations, security checks are either baked into heavyweight scanning tools that require separate credentials and long run times, or they're left to manual reviews that often miss subtle issues. By leveraging the same API calls that Kubectl already makes, K8's Audit stays in sync with the cluster's live state, avoiding the drift that can happen when you scan a stale snapshot. And because JQ is a pure text processor, the output can be easily parsed or fed into alerting systems like Prometheus Alert Manager. The project is still early stage, there's no official support contract, and the rule set is community-driven. But several teams at cloud native shops have already started to adopt it as a quick sanity check before pushing changes. If you're looking for a low-overhead way to catch the most glaring security gaps without adding another heavyweight scanner to your stack, give K8's Audit a spin. Just clone the repo, make the script executable, and run it against any context you have configured in your kubeconfig. In a few seconds, you'll see a list of red flags that you can then prioritize, turning what used to be a lengthy audit into a rapid, repeatable safety net. The latest GCP release notes include a small but handy fix for a Pidgey's management console. If you've been building API proxies in a Pidgey, you'll know the service callout policy is the way you let a request invoke an external service. Think of it as a built-in HTTP client that can enrich a request or response with data from another endpoint. Until now, when you tried to add that policy through the Pidgey UI, the workflow would stall. After picking Service Callout from the Create or Add Policy pane, the dialog would only show the name and display fields, and the Create button stayed grayed out. In practice, that meant you had to drop back to the XML editor, paste the policy snippet manually, and then resync the UI, a clunky step that broke the promise of a visual, drag-and-drop experience. The fix, identified as bug 543,626,585, restores the full form for service callout in the UI. Now when you select the policy, the panel correctly expands to include all the required fields, like the target endpoint URL, request template, and any response mapping you need. The Create button becomes active as soon as the mandatory fields are filled, letting you add the policy with a single click. For day-to-day engineering, this change reduces friction in the development cycle. Teams can stay in the graphical interface longer, avoid context switches to the raw XML editor, and catch configuration errors earlier because the UI now validates inputs in real time. It also smooths onboarding for newer engineers who might not be comfortable editing the underlying proxy definition directly. Larger organizations that run dozens of proxies, think financial services or retail platforms that rely on a Pidgey for traffic management, will see a modest boost in productivity, especially when iterating on complex callout logic. The fix doesn't introduce new features, but by closing that usability gap, it helps keep the Pidgey experience consistent with the rest of Google Cloud's emphasis on developer-friendly tooling. Now, let's shift gears for the Architect's Corner. 5 minutes on real enterprise software architecture and system design. The team behind a large e-commerce recommendation service hit a wall when they tried to add a conversational AI layer on top of their existing data platform. Their product catalog lived in Amazon DynamoDB, and they already had a set of microservices that queried that table for things like price, inventory, and product attributes. The new AI feature needed to do two things at once: retrieve exact, structured records when a user asked for a specific SKU, and also perform semantic search, finding products that feel like a user's description, even when the exact keywords didn't match. The naive approach they first tried was to spin up a separate vector database, dump the product embeddings there, and keep it in sync with DynamoDB via a nightly batch job. That introduced a host of problems. First, they now had two sources of truth. Any lag in the batch meant the AI could surface stale or missing items. Second, the operational overhead of provisioning, scaling, and backing up a third data store was non-trivial, especially given the team's already tight DevOps bandwidth. Finally, latency suffered because the AI service had to make two round trips, one to the vector store for the semantic match, another to DynamoDB for the full product record, adding milliseconds that mattered in a real-time chat experience. What they needed was a unified store that could handle both exact key lookups and vector similarity search, while staying consistent with the rest of their data pipeline. The breakthrough came when DynamoDB announced native vector search capabilities. Instead of treating embeddings as a separate concern, they could now store the embedding alongside the regular attributes in the same table, using a special vector index that DynamoDB builds under the hood. The team re-architected the flow around three core components: the data ingestion pipeline, the DynamoDB table with a hybrid index, and a DynamoDB streams-driven update path. When a new product entered the catalog, the ingestion service first wrote the structured fields, SKU, price, category, to DynamoDB. Immediately after, a Lambda function called Amazon Bedrock's embedding model to generate a dense vector representation of the product description. That vector was then written back to the same DynamoDB item, populating the new vector attribute. Because the vector lived in the same item, any query that needed both the exact SKU and the semantic similarity could be satisfied with a single getItem or query call, specifying either a primary key condition or a vector similarity filter. Keeping the vector in sync when product data changed was the trickiest part. DynamoDB Streams captures every write, update, and delete operation on the table. The team set up a second Lambda that listened to those streams. When a product's textual description was updated, the Lambda re-invoked the Bedrock embedding model, overwrote the vector attribute, and let DynamoDB's internal index refresh automatically. For deletes, the Lambda simply let the item disappear, and the vector index pruned the entry. Because streams are near real-time, the latency between a content change and an updated semantic search result dropped from hours to seconds. The final architecture looked like this. A front-end chat service sends a user query to the Bedrock agent. The agent decides whether the request is a structured lookup, show me SKU 12,345, or a semantic one, find me a lightweight running shoe for summer. For structured requests, it issues a standard getItem on the DynamoDB table. For semantic requests, it sends the user's query text to the same Bedrock embedding model, gets back a query vector, and then runs a DynamoDB query with a vector similarity filter. DynamoDB returns the matching items, already enriched with all the operational fields, and the agent formats the response for the user. All of this happens within a single managed service stack: DynamoDB for storage and indexing, Bedrock for embeddings, and Lambda for the glue logic. Why does this matter for an enterprise architect? First, it illustrates the power of co-locating AI-specific artifacts. Embeddings, with the core operational data. By avoiding a separate vector store, you eliminate data duplication, reduce operational complexity, and get a single source of truth that is automatically backed up and replicated by DynamoDB's existing mechanisms. Second, the pattern leverages fully managed services, meaning you don't have to provision, patch, or scale a dedicated vector database. DynamoDB's auto-scaling and on-demand capacity handle the load, and the vector index scales alongside the table. Third, the streams-driven update loop gives you near real-time consistency without a heavyweight ETL pipeline, which is a common pain point when trying to keep embeddings fresh. Of course, the approach isn't a silver bullet. DynamoDB's native vector support comes with limits on vector dimension size and the number of vectors you can index per partition key, so you need to model your data to stay within those constraints. Throughput planning becomes a bit more nuanced because each write now carries both the structured attributes and the embedding payload, which can increase write capacity units. The streams-based Lambda introduces eventual consistency. There is a small window where a query might see a stale embedding after a description change. Finally, the cost model shifts. While you avoid a separate vector store, you pay for the additional read-write capacity and the bedrock embedding calls, which can add up at scale. The takeaway for architects designing enterprise AI-enhanced systems is to ask early whether the vector data truly needs its own store or can live alongside the primary entity. If your use case involves frequent joins between semantic results and transactional attributes, a unified table can simplify the architecture dramatically. When you do choose this path, plan for the operational trade-offs. Size your tables for the extra payload, monitor streams latency, and design your Lambda functions to be idempotent and resilient. By doing so, you get a low-latency, consistent, and maintainable system that lets AI agents answer both, "What is this?" and "What is similar to this?" without juggling multiple databases. This pattern is especially compelling for product catalogs, knowledge bases, or any domain where structured metadata and unstructured text coexist and need to be queried together. And that's your briefing for today. See you tomorrow morning.